Hello everyone, my name is Gustavo Bitencourt. I'm going to explain a little about this work called Comparative Study of Different Synthesis Routes of Iron 88B and Amino Iron 88B Metallic Granite Frameworks applied to the direct methane oxidation to methanol under mild conditions, which is a part of my PhD project. So to bring the context, we must know how the energy sector works. It's basically sized to supply all these minor sectors, and all of this is basically powered by fossil fuels. And what's the problem involved in this? Well, about 80% of the world's energy demand is food from fossil sources, which generate excessive emissions of greenhouse gases, which end up generating several complications worldwide. Well, as my project is associated with the conversion of methane through metallic organic frameworks, it is important for me to do more targeted analysis for natural gas, which is mainly composed of methane and other gases. And the importance of methane to the industry is remarkable, since it serves as a precursor material for the generation of various chemicals used in everyday. And this is the main purpose of this work, which is trying to produce a more direct way of conversion of methane to high added value chemicals like methanol. So in this context, I selected the metallic organic framework iron mu 88B and amino iron mu 88B, and we tried three different routes of synthesis. The first one was using the organic linker terephthalic acid for the 88B and the 2-amino terephthalic acid for the amino 88B, while the metal precursor was the iron chloride and the modulator of the reaction was the polyvinyl pyrrolidone solution. And all this was dissolved in dimethyl formamide. Then all the reagents were mixed in a flask and reacted at 145 degrees Celsius for 19 minutes with magnetic stirring. After this, the resulting moths were washed with ethanol and dried overnight. For the second synthesis, we switched the metal precursor for the iron chloride hexahydrated, and no modulator was used. Also, the synthesis system was changed for an autoclave that stayed at 170 degrees Celsius for 24 hours without magnetic stirring, and then the same steps were repeated. And for the last one, the third synthesis, it was basically the same of the previous one, but we changed the temperature for the synthesis for 130 degrees Celsius and also add the magnetic stirring for the system. Then the same steps were also repeated. As for the characterization, we did an X-ray diffraction, and all the syntheses show a crystalline structure with some minor deviations between them. And beside this, they all were relatable with the diffractograms from the literature. And for the scanning electron microscopy, we consider the first method gave us a very homogeneous and well-shaped defined crystals for the 88B, but for the amino 88B, it didn't work the same way. And when compared the second and the third method, we consider the third one shows a more defined crystal shape for both MOFs, and so because of this, we chose the third one to continue to the catalytic tests. And for these tests, we have here our reaction system and the reaction conditions that we explored, and we achieved these results. For the 88B, considering 15 minutes of reaction, methanol, acetic acid, and formic acid were produced, not showing up a selective reaction. But beside this, it's still showing up a high productivity of methanol per hour. And when we analyze the amino 88B, we can see that productivity drastically reduces, but we achieve a totally selective catalyst in 30 minutes of reaction. And even with this huge reduction in productivity, it still remains superior to some offs already reported in the literature. So this was the reference used to make and explain this presentation, and I would like to thank you all for the attention.